We will continue with the next speaker, Dr. David Murià Vila, researcher at the Engineering Institute at UNAM. Welcome.
Muy buenos días a todos. Espero que
Good morning, everyone. I hope everyone is doing great. I'm going to start sharing my screen. Just give me a moment.
¿Ya lo están viendo?
Así es, doctor, ya la estamos viendo.
Can you see it?
Voy a hacer la
Yes.
presentación. Bueno, espérenme un instante para hacer el modo presentación. Ahí está.
Let me just go to presentation mode. And I'm going to be talking about the accompaniment throughout the school reconstruction process. Now, we set up a team, a very big team of academics, specialists, professionals, specialists from INIFED, academics from the Metropolitan Autonomous University, the Engineering Institute, and private companies. And my presentation will cover the introduction, survey of damages and observed, fragility, empirical functions, environmental vibration studies, numerical models, and conclusions and recommendations. As we know, in 2017, Mexico was impacted by two big earthquakes. On September 7th in the Gulf of Tehuantepec, which affected the states of Chiapas and Oaxaca, and unfortunately there were 98 deceased persons. And very few days later, on September 19th, in the center of the country where we find more population, more densely populated areas, the earthquake affected Puebla, Morelos, state of Mexico, and Mexico City. The number of deceased people increased to 369, out of which 228 were located in Mexico City. The number of school buildings was higher, 19,000. 63% were minor damages, 36% were moderate to severe damages, and 1%, 210 schools, required the reconstruction of part or the totality of all school buildings. In the case of public schools, there were no victims. Now, the Engineering Institute partnered with INIFED and the World Bank to contribute to the gathering of evidence and the promotion of a wide and safer school program to generate knowledge based on evidence, analyzing school buildings' performance in these events in order to inform and document the recovery process. The scopes that we defined was to define a recovery strategy for school infrastructure, to propose a strategy to reduce seismic vulnerability for the new infrastructure that was going to be built or intervened, and to develop an information platform to assess the performance of buildings in earthquakes. And we set up a database. This base includes more than 12,000 buildings, amounting to 13.2% of damaged schools and 35% of schools with moderate to severe damages. We found that the quality of data varied as well as its integrity. So we will have to put an effort to increase that quality. We heard just a moment that we have created this ADN, which is a great thing. I don't know if it's covering all, but it will without a doubt be very useful for the study of damages. School buildings were classified according to the material and their prototype. The prototype means the buildings that were designed, built by INIFED and CAPFE for the past 75 years. In the database, 46% of all buildings correspond to buildings that did not belong to a prototype. Now, in these prototype buildings, we don't know the year of construction. We don't know their birth certificates, which is an important piece of information that we need to know. Now, the most impacted prototype buildings were the original prototypes, the 1, 2, or 3-story concrete buildings, and steel 1-story buildings. The damages can be attributed to a setup of details, non-ductile details, lack of constructive quality, lack of maintenance, lack of inspection. The construction age in Mexico is important. And comparing buildings in terms of damages before and after 85 is a watershed in structure design, because after the great earthquake of 1985, the indexes for earthquakes increased and ductility was the focus. So the comparison of damages pre and post 85 in the database of buildings that we have, 2/3 of those buildings are pre-85. The regional buildings, masonry buildings, don't show any difference in damage, but in the other types, there is a reduction in damages. 75% of cases registered less damages, and they all withstood the earthquakes of 2017. Regional concrete and steel buildings, they all have masonry walls, which is where the damages were concentrated. In the regional buildings, we're talking about cracks and flexion cracks. And the concrete buildings, the damage was concentrated in columns, and in steel buildings, we saw the damage of columns and beams in pre-85 buildings. In order to identify the type of damage, the quality of the information in their certificates, and to do an environmental vibration study, we carried out field inspections in Oaxaca, Morelos, and Mexico City states. I'm going to show you a series of images just to illustrate one of these concepts. We see a fence with noticeable deterioration and deficient maintenance. The regional buildings with damaged in masonry walls without buttresses, thus decreasing the strength of these walls and less performance. In this side, we see two schools right next to each other, and we found that the structures that were damaged were being rebuilt. We don't know why it was determined that they had to be demolished. But what we did see was in school B, a concrete structure.
We have one of the segments here. You can see the damage versus this structure. And on this side, you don't see it because of the branches, but you can see it right here, yes. And with those photographs, this is school B. We saw the structure here with this slab that had clashed with the neighboring school, with the one right next to it, that is. And they had built an additional classroom, therefore altering the prototype school building and turning it into an atypical school building. Now, in terms of the regional ones, they all had very good behavior. However, you see damage here. What happened was that one of the beams here was anchored or connected to the school wall. And that's what was causing all this. Here you see foundation damage, not too serious, but you can see it. Roof problems as well, and you see this door. This is the vertical damage. This was not written down when the survey wasn't on the documentation. And this, the steel structures. This is a thin wall profile, and you see this because of the low walls. But those that had a different profile, but the low walls did cause it to be damaged. Now, this, you can see this in the beams. This is a concrete structure, and there's a construction here with acceptable performance. And this was easily corrected, even with the bending of it. However, these classrooms were not being used. So that students could continue having their classes there. This is the concrete building, one-story building. There's a problem between the low walls and the column. There is a separation as the prototype regulations set forth. Moderate damage on the columns here because of the low wall. These are other buildings showing the use of inappropriate additions without meeting specifications and standards. This is lack of supervision. And here we see the rehab, the jackets, and the ties here to the perimeter. This is already included in the guidelines. In the case of reconstruction, this is an emblematic case. A lot of it was covered in the media. This is in Juchitán, a school center. It was a local collapse, no victims. It was reconstructed with two-story concrete buildings. Here we have another interesting case. You see here, demolished elements. We do not know what the structure was like, but this inappropriate additions or expansions without following specifications. In the reconstruction, they were doing exactly the same, using the same type of materials. Here, a regional one. This is regional reconstruction. The same masonry here, but no supervision. And this should be there, but it's not. Now for the numerical inspection, we checked or inspected 14 schools, regional ones, and concrete buildings. And we can see that this corresponds to the values we know of structures under good conditions, of course. Minor damage or no damage whatsoever. To give you an idea, to do damage studies, we have to look at seismic intensity and damage levels in buildings. We did an analysis in cases where we had very precise data and damage elements. Here you see the severe damage probability at the regional level vis-a-vis intensity. And this is maximum ground acceleration. Expected behavior, more intensity, more probability of damage. In this case of concrete buildings, we did not use this correlation between frequency of damage and damage intensity. Numerical models. We did numerical studies through models to see the behavior or response of the buildings. We selected a regional one, 1 to 4 classrooms, with or without retrofitting, and the jacketing of the walls. And concrete buildings, 1 or 2 story buildings, one built in 1970 and the other one 2011, with or without retrofitting of the concrete walls. Let me just tell you about the regional project we did. I don't have much more time for anything else. Now, the performance was assessed according to static analysis. I'm talking about nonlinear static analysis, capacity curves and pushover and elastoplasticity. This is the equivalent seismic force and displacement. You see it right here. As of that point, remembering these are group-based schools, we shouldn't just look at the maximum displacement that is to be tolerated in nonlinear formation as of the plastic deformation. It should be less than that to guarantee the operational part of all this. This is the capacity. You see the curves right here of this 4-story classroom, of this 4-story school, and you can see that only in these cases with type 1 soil or ground, we can see we should only inspect zone C and D with soils 2 and 3. And this is the lifespan or the limit. Conclusions. Buildings with good construction quality had good behavior. Based on analyzed information, we proposed recommendations on policies, techniques, implementation, sustainability, and to divulge all that information to minimize school seismic risk. And also, we proposed a strategy to increase seismic resistance, strengthening all this through the different experiences in different parts of Mexico, as well as implementing a program for all this. And this program should be there to reduce risk. For reduction of seismic risk, we recommend a comprehensive, systematic, and pluriannual strategy, especially for buildings made before 1985 and also atypical buildings. Design, construction, inspection, maintenance, and conservation of schools, and this should be done through guides and manuals. We know, not only through this event, but we know that conservation and maintenance are very poor and deficient. In terms of safety and rehab evaluation of structures, this should all be done through guides and manuals. The manuals are there, the guides are there, so they should be better used. In terms of training and certification of personnel, it's important to have high-skilled and qualified specialists to do those training sessions, and also disseminating strategies and actions through different government instances related to construction, inspection, maintenance, and the participation of school authorities is also of the utmost importance. Thank you so much for your attention.